All right, well, good morning. Happy Monday. And happy, I guess week 6, November. Election days tomorrow. And then, next week we have Veterans Day, so that's a holiday. But next week we also have a midterm exam in this class, so I'll have to give you a description of what to expect. This stuff we've been covering, and then after that, it feels like the remaining weeks go by really quick because week 8 is short because of Thanksgiving, and then it's like week 9 and week 10, and then I don't know. I generally leave week 10 to be like low on heavy content, just because week 10. All right. Well, anyway, let's continue on. I want to go over the island hopping example again for the Metropolis algorithm, and we'll review the island hopping example, which is a discrete case, and then we will expand from that and go to kind of the general Metropolis algorithm, which allows for a Markov chain that generates samples from a continuous distribution. So, thank you. So our example is that we have this this chain of islands, and this kind of stands as a stand-in for the state space that we have. So there's 7 different islands, and in our Markov chain, we have 7 values for our state space. And the probabilities of each of those states, at least the target distribution, is this. We want to go to state 1 with a probability of 1 over 28. We want to go to state 7 with a probability of 7 over 28, and so on and so forth. This is what our target probability distribution is. And the illustration or the example given is that the politician wants to visit the islands relative to their population size. So, the islands that are more heavily populated will get more visits, and the island that is least populated will get the fewest amount of visits, et cetera, et cetera. And so this is why this is our target distribution. And the algorithm that the politician uses, basically the set of rules. So algorithm, we keep throwing that term around, and it's often treated as like some mystery black box that we can't explain. And a lot of times we're not quite sure, but like the weights that as far as like how the app recommends what video to watch next, but we just say, oh, it's the algorithm. But basically, at its core, an algorithm is just a set of rules that we follow. And apparently, as far as feeding videos to you and things like that, the rules are driven by, user engagement, things like that. So, but anyway, basically, the set of rules that the politician will use as far as where to go next is the politician starts by flipping a coin, and depending on how the coin lands, it will either propose the island to the east or to the west. So we have a 50% probability of proposing either an island to the east or to the west. And then we have to make a decision regarding whether to visit that island that was proposed or not. So sometimes an island is proposed and we don't go there. Sometimes an island is proposed and we do go there, okay? And so if the proposed island has a larger population, then we will definitely go to the proposed island. But if the proposed island has a smaller population than the current island, we only go there with a probabilistically. And so we calculate a ratio, which is the basically the target probability, all right, of the proposed location divided by the target probability of the current location. And then that will be our P move. And that, so P proposed is less than P current. P move will be a value between 0 and 1. Then we will draw a random value from the uniform distribution. And if that value is less than P move, we will go to the proposed island. Okay? And if we don't go to the proposed island, we stay at the current island and I guess do another campaign stop. And so the current location enters, as a sample again. And this set of rules works. In the long run, the probability that the politician is on any one of the island will exactly match kind of your target probability distribution. So in our last lecture, we calculated this transition probability matrix of the Markov chain, and we said, the row represents where your current location is, and then the column represents the location that you'll go to next. So if you're currently at island 1, the probability that you'll remain at island 1 at the next turn is 1/2, and the probability that you'll go from island 1 to island 2 is 1/2, and you have a 0 probability of going to any other chain. And that basically happens is if you are currently at island 1 and you flip tails and you propose the island to the east, which is island 2, you'll go there with 50% probability. You'll go there 100% of the time, so overall probability of going there is 50%. But if you're island 1 and you flip heads, then you propose the island to the left or to the west, and there's no island there, so you'll remain at island 1. Okay, and you can kind of go through and calculate all of these things, and we spent some time on Friday doing this, and this was our transition probability matrix. We said, and if you kind of look at this, the Markov chain as designed by this probability matrix, this Markov chain will be ergodic. It is possible to start at any one of these islands and end up at any of the other islands at some arbitrary point in time in the future. This chain is aperiodic because it is possible to go from an island back to itself. So if you can go from one island back to itself, that state has a period of 1, and then your entire chain will have a period of 1 or will be aperiodic. So our chain is irreducible and aperiodic, which means there will be a limiting distribution, and that limiting distribution will be the stationary distribution. And that stationary distribution can be found by finding the left eigenvector of this matrix. And so we did that, and we found the left eigenvector of this transition probability matrix, and it was equal to our target distribution. Okay, I said what we didn't do was actually run the Markov chain, but I think we actually did. So what we're going to do is we'll flip a coin, propose the next island, we'll calculate this probability of moving, and then we will decide to move or not. And so this is kind of an important step that sometimes students forget to do when writing code for their own Metropolis algorithm is if you don't move, your current state goes in as still your next generated random sample. So if you're at time 15 and you're currently at 5 and you don't move, then you generate a sample of 5 again for time 16. Okay, or whatever it is. Okay, so we have this function propose, which just takes your current state and will propose basically the state plus or minus 1. Okay, so if you are at state 5, it will return either a 6 or a 4. If you're at state 7, it will return either an 8 or a 6. If you're at state 1, it'll return either a 2 or a 0 or something like that. Okay. And the probability, this function p, gives us basically the probability, the target probability, which is just basically this, okay? It's just going to return this, basically the value divided by 28 if x is a value between 1 and 7, it will return x divided by 28. And if x is anything other than 1 through 7, there's no probability of going there. So if x is an 8, like you're currently at 7 and the proposal function returns an 8, this will return a 0. Okay? If your proposal function returns a 0 or whatever, then it will return a 0. Okay, so anyway, we'll try 1,000 iterations. I'm going to start the island at location 4. And then I've got 999 NAs, and we will run our chain. So my current value is currently 4. I propose using 4. Propose will either be a 5 or a 3. Then my p move, I'll do p proposed divided by p current. So if let's say I proposed a 5. P proposed 5 is going to be 5 over 28 divided by P current will be 4 over 28. So my P move will be 5 divided by 4, 1.25. Now technically P move is a probability, so it shouldn't go higher than 1. But if it's 5 over 4, this value is going to be 1.25. And if I compare U to P move, it's going to be less than 1.25 because U is always a value between 0 and 1. So I could put this extra statement here, but it's kind of unnecessary to say P move is the minimum of 1 and P proposed divided by P current. Okay. So I'm just going to compare U to P move. I generate a random U. If U is less than P move, so let's say my P move is 1.25 because P proposed is 5 and P current is 4. Okay. Then U will definitely be less than P moved, and then my X at the next iteration will be the proposed value of 5. Okay, and then so we'll record a 5 in for X. All right, and then if I'm at 5, then at my next iteration, I'm going to propose a value. I will propose either a 4 or a 6. Let's say I propose a 4. Then my P move will be P of 4 divided by P of 5, which is my current value. 4 over 28 divided by 5 over 28, I'm going to get a P move of 80%. Let's say I generate a random U. Let's say the U I generate is 0.6. 0.6 is less than 4, or 80%. 0.6 is less than 0.8. So I will accept it, and my proposed value of 4 becomes my next thing. So I'll go 4, 5, 4, and so on and so forth. And sometimes maybe I'll propose a 3, but then I reject it. Okay? In that case, my current value of 4 gets repeated. And we can let it run 1,000 iterations, and it looks something like this. And I guess this is what the chain looked like. So I started off at 4, I proposed a 5, I accepted it. I proposed a 6, I accepted it. Apparently I proposed a 5 and I did not accept it. So 6 got repeated right here. There's 2 tiny, in this picture you get 2 dots in a row, and then 7, and then so on and so forth. Maybe I can run the chain one at a time here. So here's my P proposed, this, and let me just kind of manually run this. We're going to start off at T is 1. Okay, so right now, oops. So I started off at 4, and then I went to a 5, okay? And then so now we're going to update T. This is going to be our second iteration. So my current value is 5. My proposed value is 6. My P move is going to be 1.2. The random U I generate is 0.908. So in that case, U is greater than 0.908. So X at time T plus 1, I'm sorry, P move is 1.2, my U is 0.908, so I will, 0.9 is less than 1.2, so I will accept it. So you can see my X, the next value for X is now 456, okay? And then so I'm gonna iterate to T equals 3. This is the manual way of testing out if your loop is working, okay? So my current value is 6. Let's propose a value. We're proposing 5. My p move is going to be 5 over 6, 0.8333. The random u I get is 0.89, okay? So 0.89 is greater than 0.833. So my current, I'm not going to take the proposed value. I'm going to keep the current value. So the current value, so I get another 6. Then we'll go to the next iteration of t, okay? My current value is 6. I'm going to propose a value. The proposed value is 7, okay? So my p move is going to be greater than 1. I'm definitely going to go there. And I'm going to go, so this is what we have, 4, 5, 6, 6, 7, okay? Let's see, whoops. I ran through the whole thing. But, yeah. So we go, yeah, 4, 5, 6, 6, 7, 6, 7. So sometimes we propose lower values or we propose 8s and we just stay there. And so we kind of get stuck at 7 for a little bit and then we start to come back down. And so that's just the chain when we started off at 4. And when you let it run for 1,000 iterations, this ends up being the distribution over the states. And if you let it run even longer, say 100,000 iterations, then your distribution over states looks something like this, okay? But again, when you have such a giant sample, trying to run something like the chi-square test for a giant sample just doesn't work very well, okay? So I think maybe in one of your homework problems, I have you do a giant sample, and then it's a little bit tough to judge the things, okay? But that's what we have. Okay, let me give you your first view quiz answer, which is the letter A. A as in apple. All right. Okay, so let's generalize this. And we'll just discuss the Metropolis algorithm. And the island hopping example is an example of the Metropolis algorithm, but we want to kind of generalize to allow for even like continuous distributions. Okay. So we just need some kind of function that is proportional to the desired probability distribution. So you have a target probability distribution P, and if you have that PDF, that's great, okay? But if you don't have that PDF, that's also okay. You just need something proportional to it, which is going to be really handy in, say, Bayesian statistics. Because in Bayesian statistics, and I'll bring this up again later, but your posterior distribution, you want to find the probability distribution of your unknown parameter theta given the value that you have. This is the likelihood. You do, what's the likelihood of your data given some parameter times the prior divided by the marginal. Okay? Now remember, the marginal is a constant. So that the integral of equals 1. Okay? So this doesn't serve any purpose other than to kind of normalize this distribution so the entire thing integrates to 1. But this thing is often difficult to find. It is basically the numerator, okay? It's the numerator it's the integral of the numerator, okay? Okay, so it's it's equal to this. This is often difficult to find, but it's just a constant. It's just a constant, okay? And so we often have this. You can just take the numerator, and that'll just be f of x, okay? It's often pretty reasonably easy to get f of x, the numerator, but it might be difficult to get the full PDF that integrates to 1. You'll get something that's proportional to it, but not necessarily the thing that integrates to 1. All right, and then you just start at some arbitrary point x, okay, to be the first sample in the Markov chain. You need an arbitrary proposal distribution, which will generate new values of x if you plug in some value, some other value of x. For the Metropolis algorithm, it has to be symmetric. The Metropolis-Hastings algorithm doesn't require it to be symmetric, but we'll say that it has to be symmetric, that the probability of proposing x of a given x of b is the same as the probability of proposing x of b if you start off at x of a. And for each iteration, this is what we do. We generate a proposed value based on your current value. This is the equivalent of flipping a coin and proposing the island to the left or to the right. However, we now have a continuous distribution. So perhaps you start at location 1.0 and maybe you propose the value 0.8 or 0.75 or 1.3 or 2.6 or something. Okay, so you start off at a location and you're going to propose another location, and this proposal distribution maybe generates continuous things. And then we're going to calculate the probability of moving to that proposed location. You take f of the proposed location divided by f at the current location, right? And if that's greater than 1, your probability of moving is just going to be 1. But if it's less than that, we'll take that. And then we generate a random u between 0 and 1, and we'll either accept the candidate location, the proposed location, or we will reject the proposed location. And that's that, okay? So same thing as the island hopping example, except in the island hopping example, we flipped a coin and we went either +1 or -1. And here we are using some distribution g that proposes kind of continuous values, okay? So yeah, f only needs to be proportional to p because if you have f is equal to some constant times the target distribution, you can see that the probability of p move is the same as using the target probability, right? Because you have f is c times the target probability of the proposed location times c times the target probability. And so even if you don't know this exact quantity, which is often the case, we know that just using the numerator is going to be proportional to our target distribution there. Okay, so this is what I have here. So probability of theta given x is this, and we often don't know exactly what this quantity p of x is. And so instead of trying to figure this out, we just take the numerator, which is proportional, okay? Proportional to p of x, and we use that, right? And that's going to be huge in Bayesian statistics because, again, this quantity down here, sometimes incredibly difficult or perhaps impossible to find. And I've got an example, I don't know, we'll look at it next week maybe the following week, where we just kind of have this slightly silly target PDF, but yeah, it's this quantity down here, not really possible, not really feasible to find in real life. But that's okay. We just use the numerator, and we just go along with life. Okay, so we have. So what do we do with this proposal distribution? How do we decide what values to propose? So for the Metropolis algorithm, the proposal distribution has to be symmetric, and so some common choices are the normal distribution centered at your current location with some arbitrary arbitrary value sigma, okay? So we're going to say, well, I guess we can just use this, right? So you have to propose a random location based on your current location. So we're going to say, I'm going to use our norm to generate one random value, okay? And the mean is going to be my current location x at time t, okay? So I'm going to just, if I'm currently at 0, I'm going to do our norm. And if, sigma is 1, I might generate any value between, say, -2 or +2. Technically, any value from negative infinity to positive infinity, but 95% of the time it will be a value between plus or minus 2, okay? And then, that's based on our current location. If in the future my current location is 3.7 or whatever, then I will generate another random value, maybe anywhere from, I guess, 1.7 to 5.7 or things like that. So this is, we use our norm to generate a random value. So this is, you are not calculating a probability. You're not using like the PDF, and you're not using, or the CDF. You're not calculating a probability. You are generating a random value. So this is kind of the Monte Carlo aspect of this, is that there's a random number generation. So it's really difficult to do like a Monte Carlo Markov chain yourself, Markov chain Monte Carlo manually, because as humans, we don't really have a way to generate random values, right? You can flip a coin, but generating a random normal value as a human, kind of hard to do, okay? But so we rely on the computer to do something like R norm, okay? So that would be a normal distribution centered at your current location x at time t. You can also use a uniform distribution, and you just have some arbitrary width of basically 2c plus or minus c. So you can say, okay, if I'm currently at 0, maybe I'll generate a value from -1 to +1, okay? Or if I'm currently at 5, maybe I'll generate a value from 4 to 6 or something like that, okay? So here we just would do our unif, random uniform value. I just want one of those values, and the lower bound and the upper bound are given by our current location minus c and our current location plus c, okay? And the normal distribution is symmetric, uniform distribution symmetric, so this satisfies the symmetric distribution requirement. So if our target distribution, let's say, is a normal distribution centered at 15 with a standard deviation of 3, the PDF of the normal distribution is this, okay? And in our computer, we could use dnorm, and that will give us the PDF, right? So we could use dnorm. But just to illustrate that you don't actually need the actual PDF, I'm going to just get rid of this front normalizing constant, the 1 over sigma root 2 pi, okay? It's not necessary in our thing. So I'm just going to do e to the negative, just this part here, okay? E to the -1/2 x minus 15 over 3 quantity squared. Okay, so we're going to ignore this kind of normalizing constant, and this will be our function f of x that we use to calculate our probability of moving. And then the proposal distribution, I'm going to use a uniform distribution centered at x at time t, but will generate a value between -3 and +3. Okay, and so this, and to illustrate kind of the power of the Metropolis algorithm, I'm going to intentionally start with a terrible location of 100, okay? So let's think about our target distribution. We want our data to follow a normal distribution centered at 15 with a standard deviation of 3. So 95% of our values are going to be 15 plus or minus 6. So 95% will be between, 9 and 21? And then 99.7 will be between plus or minus 9, what? 6 and 24, okay? So 24 is like 3 standard deviations above 15. And here I'm at 100. 100 is what? 85 over 15? So it's like, I don't know, 28 standard deviations away from the mean or something? Okay, so it's terrible, right? But what we'll see is we'll run the chain, okay? So here this is our algorithm, okay? F is going to be e to the negative 1/2 times x minus 15 over 3 squared. Okay, so this is just a function that is proportional to the PDF. It's not, I could have used the actual PDF and I could have done d norm, but this will just give me something proportional to it. And then my proposal function is going to just generate a random value, okay, between our current location plus or minus 3. And let me just kind of illustrate how this is going to work. All right, so let's clear this out. All right, so here's my target thing here. Okay, so let's do t at time 1. So I'm going to start off, my current location is 100, all right? And I'm going to propose a random value, basically between 97 and 103 is, because I'm taking my current, so the proposed location, I'm going to propose 98.59. And I want to know, okay, what is the probability of moving to 98.59? Okay, so we're going to calculate f at the proposed location divided by f at the current location. Well, because 98.5 is closer to 15, the mean, right? So remember, f is x minus 15 squared. So because 98 is closer to that, this p move is going to be greater than 1. P move is ridiculously big, 528,000, okay? And then I'm going to say, okay, well, should I move there? And it's going to say, yes, definitely you should move there, okay? Definitely you should move there. So we will accept that proposed location of basically 98.6, okay, as my next value in x. All right, now I'm going to do t is at time 2, okay? So my current location is now 98.6 basically. I'm going to propose another location. This time I'm proposing to move away to 99, okay? And so we ask, should I move to 99, okay? The probability of moving to 99 is not 0, but it's a pretty small number, 0.017, okay? So we're basically going from 98.6, should I move further away from 15? And it says, probably not, okay? If you're gonna move there, it should happen only less than 2% of the time, okay? So I generate a random u. My random u is 0.9, I'm not gonna go there. So my next iteration, I'm gonna be at 98.6, okay? I reuse the current value. We'll go to t time 3. So my current value is still the same, 98.6. I propose another location. I'm proposing 96.8. Should I move to 96.8? It says yes, definitely move to 96.8. Okay, and then so my next location 96.8, and then what am I? T at time 4 now. Okay, now I propose a new location. This time I'm proposing 99.47. Should I move there? It says definitely not. 10 to the minus 11. Okay, definitely not. So we reuse 96.8 again. Okay, t at time 5, and so on and so forth. So I'm currently at 96.8. I'm going to propose a location here. I'm 97.57, which is still farther away. I say, should I move there? And it says probably not. 0.0008. Okay, so we're not going to go there. We don't go there. Okay. And we keep kind of trying this out, and we say, all right, what do you propose next? Here I propose 95.03. Should I go to 95.03? It says definitely go to 95.03, okay? And so after a few iterations, we went from 100 to 98.59. We got stuck stayed there one more iteration, then we went to 96.8. Then we stayed at 96.8 for a couple iterations, and then we moved to 95.0. And so you can see, even though I started at 100, in the beginning, I'm moving closer and closer and closer to where I need to go. It's taking a while, but I do, okay? And so this is what my chain looks like after, say, the first 500 iterations or so. So here I can just kind of, all right, so I can look at kind of like my first 20 iterations. Right, so I start at 100, then I went to 98.5, or yeah, 98.6, 96.8, 96.8, 96.8, 95.03, 95.03, 95.03, 95.03, then 94.3, 94.3, 94.3, 92.9, 90.0, 90.0, 89.89, 89.85, 89.85, and so on and so forth, okay? That's just kind of the first 20 iterations, and you can see this is kind of the trace of the thing. We start off at 100, and you can see the Markov chain slowly but steadily moves down, okay? And it keeps kind of getting closer. You know, on rare occasion, all right, there's like a tiny little bump here. It means it moved away, right? So we were currently at like 61, and we proposed like 61.5, farther away from the mean. And, the probability of moving away is not 0, okay? So sometimes it does, but most of the time, it just keeps moving closer and closer and closer, right? Until we get around, remember, our target distribution is centered at 15, 95% of our values are between 9 and 21. Okay, and so when we get to that zone of around 9 to 21, then we start going back and forth. Okay, we're at 15 and we propose 17. We say, should we go there? Yeah, sometimes we go there. Okay, we're at 17 and we propose 16. We go to 16. We're at 16. We propose 16.5. We go to 16.5. We're at 16.5. We propose 13. Sometimes we move there. Okay, and so we go kind of back and forth. Okay, but if we're say at I don't know, 9, okay? And again, remember, 95% of our values are between 9 and 21. Let's say I'm at 9 and I propose going down to 7, okay? I don't go there, right? It kind of goes down and then it says, okay, the probability of us being down at 7 is really low, so we shouldn't go there, okay? And so we kind of start bouncing around here. And so this is... Okay, so we start off at 100, but despite starting off at this terrible location of 100, after, I don't know, after around 180 iterations or so, okay, we kind of found the location where we ought to be. And so we call this part, the part where we're kind of seeking out where we're supposed to be, we call this beginning part the burn-in period. All right, the burn-in period, we just throw this away. This is not part of our target distribution. We recognize that. We say this is kind of, I didn't know where to start, but I trust in the algorithm, and the algorithm is eventually going to find where it needs to go, okay? And when it finds where it needs to go, once it finds where it needs to go, then we're going to look at the values it generates. But until then, we're just going to kind of ignore the beginning part, okay, because it's searching around. So it searches around, then it finds it, and then we keep these values. So if I throw away the first 180 values or so, and I just kind of start from here, and I say, hey, what kind of values did you generate? What kind of values did you generate? These are the values it generated, okay? And this, you create a histogram of it compared to the values I generated. So here, the x I keep, I just throw away 1 through 180. And then I said, make a histogram of that. This looks decently like the target distribution, okay? Centered at 15, standard deviation of 3, okay? This is what it should look like, and it kind of matches that. I can do a comparison between the empirical CDF in the black line and the theoretic CDF in the red line. Matches pretty closely, okay? And that's what we have. All right. The ideal scenario is we are able to generate values from our target distribution, and they look like their IID values, okay? That's the ideal scenario. So this is, if I said, give me some independent, identically distributed values from the normal distribution, some IID values, I'm just doing our norm. This is what our norm values look like, okay? So these are IID. My values don't look like that. They look like this, okay? Because we're doing a Markov chain. The next value depends on the previous value. So they're not IID. They're not independent of each other. The next value depends on the previous value. Okay? So this is what my Markov chain looks like after I threw away my first 180 values. Okay? And so kind of on the same scale, 0 through 1,000. Okay, 0 through 1,000. So this is IID. This is what my thing looks like. Okay, and here you can kind of trace a little bit more of a path where the next value depends on the previous value. Okay, and so you can try altering your proposal distribution. All right, let me give you your next answer. Next answer is the letter C. C as in cat. C as in cat. Okay, so this is what our thing looks like using my uniform. If I use the uniform distribution to propose a new value, okay? And I'm gonna just show you some terrible proposal distributions, okay? So sometimes you have a proposal distribution that just proposes too many bad values, okay? So this proposes a uniform distribution, and it's got a width of 100. So it's going to go like plus or minus 50. So if I'm currently at, like, let's say I start in the target location at 15, but I might propose values as low as negative 35 and as high as 65. Okay. So if I'm currently at 15 and I say, hey, should we go to positive 65? The algorithm is going to say, no, definitely not, right? Because again, 95% of our values are between 9 and 21. So do I ever want to go to 65? No, I'm never going to go to 65, okay? And if I'm proposing values between minus 35 to positive 65, there's only kind of a, this smaller window of 9 to 21 are like reasonable values. And so this is my proposal thing. I'm going to go start at my current location, and we'll go plus or minus 15. I'm going to start at kind of like where I know values should be generated at 15. And I say, okay, let's just propose a value. Let's see if we go, and we run the chain. And our chain looks like this, okay? Now, theoretically, if you could run this chain forever, it will look like the target distribution, okay? Theoretically, it is ergodic. It will reach a limiting distribution. It will reach a stationary distribution. It's just, this chain is really inefficient, okay? Because what happens is you start off at 15 and you propose values that just aren't going to get accepted. So let's say I'm currently like in this, here we see this flat line here. That means I was at 15 and I kept proposing terrible locations that got rejected. So I proposed 60, we rejected it. I proposed negative 30, we rejected it. I proposed 55, we rejected it. I proposed 2, I rejected it. I proposed 24, I rejected it. And basically I got stuck here because every time you reject it, you just reuse your current value. So I'm currently around like 15.2 or whatever, and I'm proposing all of these terrible locations. We reject every single one. So 15.2 just keeps going into our values of things, of values, random values that we generated. And then finally, I said, okay, well, what if I propose 13? And we say, okay, 13 we'll accept. And then we move there. And then we proposed a few, and then we rejected them. And then when I say, okay, well, what if I propose, I don't know, 16 and a half? We accepted that. What if I propose 21? I accepted that. And then so it kind of bounces around, and then again, we get stuck for a little while and we get stuck for a little while, okay? So you kind of have this, looks like a city skyline where you have these flat regions where you get stuck because all of the values you keep proposing get rejected, okay? Okay, that's if you have a proposal distribution that proposes just bad values, okay? Here, I have a proposal distribution where the values I propose will either be plus, my current value plus 0.5 or my current value minus 0.5, okay? So I have a width of 1. So if I'm at 15, I might propose 15 and a half, I might propose 14 and a half, I might propose 15.2, 14.8, something, you know, from 14 and a half to 15 and a half, okay? What happens here? Okay, basically, if you think about what is my proposed location wherever it is really close to my current location because I'm only going to deviate from it by plus or minus 0.5. Okay, so if the proposed location is really close to my current location, then my p move, the probability of moving, remember, is f at the proposed location divided by f at the current location. F at the proposed location divided by f at the current location will be ends up being close to 1. Okay, so you know, with the normal distribution, your peak is at the mean, okay, of 15. But if, let's say I propose 14.9, okay, what's the difference between the density at 14.9 and the density at 15? It's they're very, very close to each other. So you're gonna get a p move of like 0.98, okay, 98%. So you're gonna, if I propose 14.9, I'm gonna accept it 98% of the time. So like, what happens here is that almost every single value I propose gets accepted, okay? And I just take these tiny little steps up and down, tiny little steps up and down. And so the values that I generate look kind of like this, okay? So this is kind of like, you know, some wild stock going up and down, small moves, every single kind of, at every iteration. Okay, so nearly every proposed value gets accepted, and the chain only moves in tiny increments, and this looks a little bit more like a random walk, and the chain basically drifts into regions of high and low probability and things like that. And again, in the long run, it will converge to where it's supposed to be, but it's inefficient because you kind of just wander aimlessly throughout the distribution, okay? Here's something that's kind of, you know, all of these things you're looking for like the Goldilocks solution, somewhere kind of not too big, not too small, just right. And so, you know, here's one where I have a width of 12 plus or current value plus or minus 6. These are all our UNIF. And when we do that, this is kind of what my my chain looks like, okay? Remember that the ideal scenario is IID. IID looks like this, okay? This is my width of plus or minus 3, and here's my thing with plus or minus 6, okay? And so, you know, I would say this looks kind of closer to the IID results than any of the other ones with a plus or minus 50 or plus or minus 1/2, okay? But yeah, it sometimes it takes a bit of guessing to try to figure out what kind of proposal distribution to use, and then you want to kind of look at what kind of values you generate and get there. Okay, well, that's it for today's lecture. So we'll wrap it up here, and let me give you your last ViewQuiz answer.